Look up tonight and find the sun is the most ordinary thing in your sky and the most misunderstood. Ask most people how it dies, and they will describe an explosion, a white flash, a shock wave, the planet swept away in a single violent instant. That picture is wrong, and here is the number that proves it. The sun weighs 330,000 times as much as the Earth, and it is still far too small to ever explode. That should stop you for a moment. The sun is 330,000 Earths, poured into one ball of fire. It holds 1,000,000 Earths inside its volume with room to spare, and by the standard that decides whether a star can detonate, it does not even come close. A star that ends in a true explosion, a supernova, needs to be born with roughly 8 times the mass of the sun. The sun carries one. It is a lightweight. It always was. Before we go further, a small thing. If you find these slow walks through the real physics of the sky worth your evening, a like or a subscribe helps more than you would guess, and the channel is on Spotify too if you drift off better with just a voice. That is the whole ask. Now settle in and let the sun tell you the truth about itself. Start with what most people imagine, because the image is powerful and worth dismantling slowly. In the popular version, the sun ends the way stars end in films. It swells, it flares, and then it bursts, scattering the solar system in a wall of light. It is a satisfying picture. It has drama, symmetry, a clean and final ending. It is also physically impossible for a star built like ours. The sun cannot do it. Not in 1,000,000,000 years, not in 1,000,000,000,000. The machinery required simply does not exist inside a body this small. To understand why, you have to understand what a real explosion demands. A supernova is not just a big fire. It is a specific catastrophe with a specific cause, and that cause has a mass requirement written into the laws of physics. When astronomers say a star needs about 8 solar masses to explode, they are not guessing at a round number. They are describing the point at which a star can build the one thing that triggers collapse, an iron core. The sun will never build one, and a star that cannot build an iron core cannot detonate. That single fact decides the whole story. Hold on to the contrast for a moment, because it is the heart of tonight. Picture a real supernova. When a massive star dies this way, it does something almost impossible to hold in your mind. For a few weeks, that single dying star shines brighter than its entire galaxy. Not brighter than a neighbouring star, brighter than 100 billion stars combined. One point of light outshining the whole disk that contains it. From across the universe, telescopes catch these flares and know instantly that a giant has fallen. Now set that beside the sun's real ending. There is no flash. There is no wall of light. There is no sound, and there would be nothing for a distant observer to catch. The sun's death is silent and slow, a softening of light spread across hundreds of thousands of years. It is less an explosion than an exhale. Where a supernova is the loudest event in a galaxy, the sun's end is one of the quietest things a star can do. 2 deaths could hardly be more different, and the difference comes down to weight. So let us follow the machinery of a star that can explode, because seeing what the sun lacks is the clearest way to see why it is safe. Inside every star, including ours, a war is fought without pause. Gravity pulls inward, trying to crush the star into a point. Fusion pushes outward, the heat of nuclear burning holding the weight up. For most of a star's life, the two are matched, and the star simply shines steady and calm. The sun has been holding that balance for about 4.5 billion years. It will hold it for billions more. In a massive star, one born with 8 times the sun's mass or more, that balance leads somewhere the sun can never go. A heavy star burns hotter and harder. It fuses hydrogen into helium, then it fuses the helium into carbon and oxygen, and it does not stop there. The crushing weight of all that mass drives the core to temperatures the sun will never reach, so the burning climbs: carbon into neon, neon into oxygen, oxygen into silicon, and silicon at last into iron. The star builds itself in layers, like an onion, each shell burning a heavier fuel than the one outside it, all of them wrapped around a growing core of iron at the centre. Iron is where the story turns. For every step up that ladder, fusion has paid the star back. Fuse light elements together, and energy pours out. That outward flood of energy is what holds the star up against its own gravity. But iron is the flaw. Iron is the most tightly bound nucleus there is. Try to fuse iron into something heavier, and the reaction stops giving energy and starts taking it. The iron core burns nothing. It only grows, a dead weight at the centre of a star, producing no heat to hold itself up. Now the war has only one possible ending. The iron core keeps gaining mass as the shells above it keep burning, and it produces no outward push of its own. It leans on one last support, a strange quantum pressure we will come back to, and there is a hard limit to how much that support can carry. When the iron core crosses that limit, gravity wins in an instant. The collapse is almost too fast to describe. In less than a single second, a core larger than the Earth falls inward and crushes itself into a ball of neutrons about 1.5 times the mass of the Sun, squeezed into a radius under 6 miles. A whole stellar core folded down to the size of a city. That collapse is the trigger. The infalling matter slams into the new neutron core and rebounds. A flood of ghostly particles called neutrinos pours out of the crushed centre, and that neutrino wind helps drive a shockwave back up through the star. The outer layers are blown apart. That is the supernova. That is the flash that outshines a galaxy. And every step of it depends on one thing the Sun will never have. An iron core heavy enough to fall. Here is the number that keeps the Sun safe, and it deserves a slow moment. That last support inside a dying core, the thing gravity has to overcome, is called electron degeneracy pressure. It has a ceiling, a maximum mass it can hold up, and that ceiling is named the Chandrasekhar limit. It sits at about 1 4/10 solar masses. Below that limit, the pressure holds and the core survives. Above it, no amount of that quantum pressure is enough. Gravity takes over and collapse cannot be stopped. 1 4/10 solar masses is the line between a star that settles quietly and a star that detonates. Now weigh the Sun's future against that line. When the Sun reaches its own end, it will not leave behind 1.5 solar masses of iron. It will leave a core of carbon and oxygen weighing only about 5 or 6/10 of a solar mass. That is roughly 1/3 of the Chandrasekhar limit. The Sun's remnant will sit far below the collapse line with an enormous margin to spare. There is no path by which the Sun's core reaches the mass it would need to fall. The trigger is not merely unlikely, it is absent. And it is absent for a simple reason. The Sun will never burn its way up the ladder to iron. It does not have the weight to drive its core that hot. The Sun will fuse hydrogen into helium, as it does now, and later in its life it will fuse helium into carbon and oxygen. That is as far as it goes. Carbon and oxygen are the end of the road for a star this small. It will never fuse carbon into neon. It will never reach silicon. It will never forge a single ounce of iron. The onion of heavy shells that a massive star builds is something the Sun cannot even begin. Without the ladder, there is no iron core. Without the iron core, there is no collapse. Without the collapse, there is no supernova. The chain that ends in an explosion is broken at the very first link. Sit with how strange that is. Everything about the Sun feels overwhelming. Its light crosses 93 million miles of empty space and still burns your skin. Its core runs at about 27 million degrees Fahrenheit. It has shone with that heat for billions of years and will shine for billions more. By every human measure, the Sun is vast beyond comprehension. And yet, by the standard that decides how a star dies, it is small. It is gentle. It is, in the honest language of astronomers, a lightweight. To earn the ending that science fiction trained you to expect, the Sun would need to be a completely different star. not a little heavier, roughly 8 times heavier. You would have to gather 8 suns and pour them into one to reach the low end of the range, where explosions become possible. And even then, the exact threshold shifts with the details, somewhere around 8 to 10 solar masses depending on what the star is made of and how much mass it sheds along the way. The Sun is nowhere near that door. It was born too light to open it, and nothing in its future adds the weight it would need. This is why the exploding Sun is a myth, and a revealing one. The image is borrowed from a different kind of star, a rare and heavy kind, and stapled onto our own quiet one. The real Sun is common. Most stars in the galaxy are like it, or smaller. Vast explosions are the exception, reserved for the giants, and giants are rare precisely because it takes so much mass to become one. When you look up at the Sun, you are not looking at a bomb with a long fuse. You are looking at a star that will end the way most stars end, without a single loud moment. There is something almost tender in that. Once the fear of the explosion is gone, the Sun will not tear the solar system apart in a flash. Whatever happens to the Earth, and that is a genuine question with a genuinely surprising new answer, it will not happen in a wall of fire scattering the planets to the dark. The Sun's end is not an event. It is a long, slow settling, gravity doing patient work over spans of time that dwarf every empire and every ocean. The drama is real. It is simply drawn out across a scale you were never built to feel. And the ember it leaves behind will be stranger than any explosion. Picture the Sun's final core, that half a solar mass of carbon and oxygen, exposed at last and glowing white hot. It will be about the size of the Earth, packed with the mass of half a sun cooling in the silence of space. No fuel left to burn, no outward push except the same quiet quantum pressure that held its collapse in check. Just an Earth-sized coal, radiating away its last heat across a stretch of time longer than the universe has so far existed. That is the true shape of the Sun's death, not a bang, a fading. So let the Hollywood image go. There will be no detonation, no shockwave, no galaxy outshone for a few brilliant weeks. The Sun does not carry the weight for it, and it never will. It cannot climb to iron, so it cannot build a core that falls, so it cannot explode. Everything you were taught to fear about the Sun's ending belongs to other stars, the heavy ones, the rare ones, the giants that die loud. Ours will die quiet. The only question left is a better one. A question about what a small, calm, ordinary star actually does when its long life finally runs out. That is what we will follow, and by the end of tonight the real ending will feel far more astonishing than the explosion ever did. Because the truth is not that nothing happens. A great deal happens. The Sun will swell and brighten and shed its outer layers into glowing rings. It will hide a violent event so deep inside itself that no eye could ever see it. It will end as a crystal the size of a planet. None of it is an explosion, and all of it is real, and each stage is stranger than the myth we are leaving behind. We have spent tonight clearing away the false ending so we can see the true one clearly. That is what it will actually do instead. So if the Sun can never detonate, the real question is what it will do instead. And that story begins with a light that is very slowly, almost imperceptibly getting brighter. So if the Sun can never detonate, the real question is what it will do instead. And that story begins with a light that is very slowly, almost imperceptibly, getting brighter. You have never noticed it, and you never will. But the Sun above you is not the same Sun your distant ancestors saw. It is about 4.5 billion years old now, roughly halfway through a hydrogen-burning life of some 10 billion years, and in that time it has changed. The Sun today is about 30% brighter than it was at its birth. It gains roughly another 10% every billion years, a slow and patient climb that no single human lifetime could ever feel. That brightening is the whole story. It is the quiet engine behind everything that comes next. Before we follow that light forward, let me ask one small thing of you. If you find yourself curious tonight, a like or a follow helps this channel reach other quiet minds who cannot sleep. You can also find these journeys on Spotify. That is all. Now settle back and let us keep drifting. To understand why the sun brightens, you have to look at what it is doing at its core right now in this exact second. Deep inside, under crushing pressure, hydrogen is being fused into helium. The numbers are almost impossible to hold in your mind. Every single second, the sun turns about 700 million tons of hydrogen into roughly 695 million tons of helium. Count the difference. About 5 million tons go missing every second. That mass is not destroyed. It is converted into pure energy, the sunlight that warms your skin and lights your sky. The sun is quite literally shedding about 5 million tons of itself each second, and it has been doing so for billions of years without pause. As the core fills with helium ash, it slowly contracts and heats. The fusion around it burns a little faster. That is why the light keeps rising. The sun is not steady. It is a fire growing gradually hotter as it consumes itself, and that rising light has a deadline written into it, one that arrives long before anything dramatic. The first ending is the gentle one. It is not fire falling from the sky. It is simply the sun growing too bright for the world beneath it. In about 1 3/4 billion years, that slow brightening will finally cross a line. The sun will pour out enough heat that Earth slips past the inner edge of the habitable zone, the narrow band where liquid water can exist. Once that happens, the planet begins to overheat. Water evaporates. Water vapor is itself a powerful greenhouse gas, so the air traps still more heat, which lifts still more vapor. The process feeds on itself. This is called a runaway greenhouse. The oceans do not simply shrink. They boil away into the sky and are eventually lost to space. What is left is a scorched, waterless rock, hot and bright and utterly still. Hold on to the timing here because it is the strangest part. This happens roughly 3 billion years before the sun ever becomes a red giant. The famous swelling, the swallowing of planets, the vast red ball you may have pictured, all of that lies far in the future. Earth as a living world ends long, long before the sun's dramatic old age even begins. The apocalypse most people imagine is not the one that actually takes the world. The real one is quieter and it comes first. By then, Earth is already a corpse of a planet. Everything that follows happens to a world that is long dead. Now let the clock run forward, past that scorched silence, to the moment the sun's core finally changes its nature. Around 5 billion years from now, the core runs out of hydrogen to burn. Fusion does not simply stop. Instead, it moves outward into a shell around the spent core, and that shell burns fiercely. The outer layers of the sun respond by swelling. The sun begins to grow. This is the red giant phase, and its scale is hard to imagine. According to a widely cited model by the astronomers Schroeder and Smith, published in 2008, the sun keeps expanding for billions of years. By about 7.5 billion years from now, roughly the year 7.59 billion in their calculation, it reaches its maximum size. At that peak, the sun swells to around 256 times its current radius. Let that number settle. A ball more than 200 times wider than the sun you know, glowing where the inner solar system used to be. But something else is happening as it grows, something that will matter enormously in a moment. The bloated sun cannot hold on to its own outer layers. It blows them off in a thick, steady wind. By the time it reaches that maximum size, it has lost so much material that it is down to only about 67% of its present mass. Roughly a third of the sun gone into space. The rate of that loss is staggering. At its peak, the red giant sun sheds mass at about 4.9 times 10 to the 20th tons every year. To give that a shape you can hold, that is close to 8% of the entire mass of the Earth flung away annually year after year. Picture what the sky itself would look like across those ages, if any eye were left to see it. Today the sun is a small, fierce, white disk. You cannot even look at it directly. But over the swelling phase, it changes character completely. Million by million years, it grows larger, and it grows cooler at its surface, and cooler means redder. The blinding white point softens into a deepening orange, then a dim and swollen red. Toward the end it would fill a huge portion of the sky, a vast, dull red wall of light where a tiny brilliant dot once hung. It would not scorch with the sharp white glare you know. It would loom, enormous and sullen, dominating more of the heavens with every passing age, a small white disk becoming a slow red ocean of light. And this brings us to the oldest question in the sun's death, the one that has haunted this story for decades. When the sun swells that far, what happens to the planets standing in its path? For the innermost worlds, the answer is not in doubt. Mercury sits far too close. Venus, only a little farther out, is not far enough. As the sun expands, both are simply overtaken. They are swallowed whole, dragged into the outer layers of the giant and dissolved. On that the models agree. Mercury and Venus are lost no matter which calculation you trust. Earth is where the certainty ends. For a long time, the standard answer was grim and simple. The influential Schroeder and Smith model of 2008 concluded that Earth too would be engulfed. As the sun expanded to that enormous radius, our planet would be caught in the outer layers and spiral inward to its end. That became the textbook fate, the doom scenario you have probably heard repeated. The sun grows, and the Earth goes with it. The reason it is not so simple comes down to a delicate contest of two opposing forces, and this is where a very new piece of science enters the story. On one side is drag. A planet orbiting inside the reach of a giant star feels a tidal pull, a friction that tends to rob it of orbital energy and draw it inward toward the fire. On the other side is that furious mass loss we just described. As the sun throws away a third of itself, its gravitational grip on everything around it weakens. A lighter sun holds its planets more loosely, and their orbits naturally widen and drift outward, away from danger. So which wins, the inward drag or the outward drift? For years the drag was assumed to be strong enough to seal Earth's fate. Then, in June of 2026, that assumption was challenged directly. A study led by Mats Esseldur at KU Leuven, published in the journal Astronomy and Astrophysics, went back to the physics from first principles. His team remodelled how tidal energy actually dissipates inside a giant star, and they found something unexpected. Inside a giant's vast, thin outer envelope, that tidal drag is weaker than earlier models had assumed. The inward pull is not as strong as the old doom scenario required. Weaken the drag while the sun is also loosening its grip through mass loss, and the balance tips. In this new picture, Earth and Mars out beyond it at roughly twice the distance may actually have what the researchers call a good chance of surviving. Not certainly, but plausibly, the planets could drift free rather than be swallowed. As Esseldur himself put it, Earth's fate depends on a delicate balance between these two effects. So here is the honest state of the question, and I will not pretend it is settled. The 2008 model says Earth is consumed. The 2026 model says Earth may quietly slip away. The disagreement hinges on a single subtle number, how efficiently tidal energy drains inside a bloated star, and that number is not yet nailed down. But even in the kinder version, do not mistake survival for rescue. If Earth does drift free, it drifts free as a dead cinder. Its oceans boiled off billions of years earlier, its air long stripped away. What survives, if anything survives, is a bare and lifeless stone, coasting past a dim red giant that no longer has any reason to notice it. The debate is not about whether the world lives. It is only about whether the corpse is buried or set adrift. That is the real, patient shape of the sun's ending. Not a blast, but a brightening. Not a bang, but a long swelling and a slow letting go. This is what it will actually do instead of exploding, a death measured in billions of years and written in shifting light. And yet, for all its scale, the swelling is not the most astonishing thing that will happen inside the sun. Something even stranger is waiting in the core, in the very moment the giant is being born. January of 2008 gave the doom scenario its most careful form. Two astronomers, K.P. Schroeder and Robert Cannon Smith, built a detailed model of the Sun as a red giant and followed it out to the end. Their numbers were sobering. The swelling Sun, they found, would reach roughly 256 times its present size. That is a body wide enough to cross the space where Earth now orbits. In their model, the planet does not escape. It is overtaken by the advancing surface, dragged inward, and swallowed whole. Their picture was more subtle than a simple wall of fire sweeping outward. As the Sun expands, it also sheds itself. At its red giant peak, it is losing mass at a staggering pace, something near 4.9 times 10 to the 20th tons every year. That is close to 8% of Earth's entire mass, thrown off into space annually as stellar wind. By the time it reaches full size, it has lost so much that only about 67% of its current mass remains. That matters, because a lighter Sun holds its planets more loosely. As the star weakens, Earth's orbit should widen, and the planet should drift outward towards safety. So even in the 2008 model, there were two forces pulling against each other. Mass loss nudging Earth away, and a second effect pulling it back. That second effect is tidal drag. As the giant Sun's outer layers bulge, Earth's gravity raises a tide in that gas, a slow, lagging swell. The swell pulls back on the planet, bleeding away its orbital energy, and that loss spirals Earth inward. In Schroeder and Smith's accounting, the inward tide won. The drag closed the gap faster than the widening orbit could open it. Earth lost the race by a narrow margin and vanished into the Sun. For most of 2 decades, that was the answer you would have been given. The planet was doomed. The only question was the exact hour of its swallowing. Then, very recently, the answer was reopened. In June of 2026, a team at KU Leuven published a paper in the journal Astronomy and Astrophysics with a plain title, The Fate of Earth During the Sun's Giant Phases. The lead author was Mats Esseldurs. His team went back to the single weakest link in the old picture, the tidal drag, and rebuilt it from the ground up. They modelled the tides from first principles, tracing exactly how a planet's pull stirs the thin, puffed-out gas of a giant star, and exactly how much of that stirring turns into lost orbital energy. What they found shifts the balance. Inside a giant star, the envelope is not solid and it is not dense. It is enormous and diffuse, a rarefied haze spread across a volume larger than Earth's orbit. In that kind of material, tidal energy dissipates far less efficiently than the earlier models assumed. The tide is still raised, but it grips the planet more gently. The inward pull that swallowed Earth in the 2008 model turns out, in this new calculation, to be weaker than anyone had counted on. And the other force has not changed. The Sun still sheds its mass. It still loosens its hold. Planets still tend to drift outward as their star grows lighter. So now you have a weaker inward drag set against the same outward drift, and the outcome flips. In the words of the lead author, Earth's fate depends on a delicate balance between these two effects. When his team ran the balance with the new tidal physics, the drift won. Earth, in this model, has a good chance of physically surviving. It is worth sitting with how narrow that verdict is. This is not a comfortable margin. It is a near tie between two vast opposing tendencies, decided by how gas you cannot see behaves in a star that will not exist for billions of years. Move one number a little, and the answer moves with it. The team is careful about this. They present survival as plausible, not certain. And Earth is not the only planet in the accounting. Mars sits at roughly twice Earth's distance from the Sun, farther out, more loosely held, easier to spare. In the new model, Mars, too, has a good chance of riding out the giant phase. But the reprieve does not reach the inner worlds. Mercury and Venus are close in, deep inside the swelling, with far less room to drift. Both models agree on their end. Whatever the tidal physics does at Earth's distance, Mercury and Venus are engulfed. They fall into the growing star and are gone. The debate that reopened in 2026 was never about them. It was only ever about Earth and the worlds beyond it. So you have two serious, published, carefully argued papers pointing in opposite directions. The 2008 model says Earth is swallowed. The 2026 model says Earth most likely escapes. Both are real science. Both were built by people who understood the physics. The disagreement between them is not carelessness. It comes down to one genuinely hard question. How efficiently does tidal energy leak away inside the thin outer envelope of a giant star? That single quantity is not yet pinned down, and until it is, the honest answer is that we do not know which paper is right. This is what a live scientific question looks like from the inside. Not a settled fact handed down, but a knife balanced on its edge, tipping one way in 2008 and the other way in 2026, and capable of tipping again when the next model, with better physics, comes along. You're watching an answer change in real time. The version you may have grown up with, the Earth devoured by the dying sun, is the older version. The newer one, more current than the story you were probably taught, says the planet may slip free. And here is the part that takes the comfort out of the reprieve. Suppose the 2026 model is right. Suppose Earth does drift outward and survive. What survives is not the world you know. Long before the sun ever swells into a red giant, the planet is already finished as a home. The rising brightness of the aging sun boils the oceans away more than 1 billion years earlier. By the time the giant phase arrives, Earth is a sterilized, waterless rock. No sea, no air worth the name, a surface scorched past anything living could endure. So the survival being debated is a strange, hollow kind of survival. It is not the survival of life, or of anything that would recognize this place. It is the survival of the stone itself. In the best case the new model offers, Earth persists only as a dead cinder, its orbit slowly widening, sliding outward past a bloated crimson star that has already killed it. A charred rock, intact, circling a light it can no longer use, keeping its distance from a sun that has nothing left to give it. That is the shape of the argument as it stands right now. One camp says the sun reaches out and takes the Earth. The other says the Earth drifts quietly away, changed beyond recognition, but whole. Neither side can close the case because the physics that decides it, the slow grip of tides inside a dying star, is still being worked out. It is one of the honest, open questions in the story of the sun's death, and you are living in the exact window where it is being rewritten. Whichever way that balance finally tips, the swelling of the sun into a red giant is only the part of its death that faces outward, the part a distant observer could see. The growing size, the reddening light, the slow reach across the inner solar system. It is dramatic, and it is visible, and it is the piece of the story most people picture when they imagine the sun's end. But the strangest moment in the sun's long death is not this swelling at all. It is a hidden fire that will ignite deep in its core and never once reach the surface. But the strangest moment in the sun's long death is not this swelling at all. It is a hidden fire that will ignite deep in its core and never once reach the surface. But the strangest moment in the sun's long death is not this swelling at all. It is a hidden fire that will ignite deep in its core and never once reach the surface. To understand that fire, you have to follow the core down. As the sun spends the last of its central hydrogen, the middle of the star has nothing left to burn. Fusion is what held the core open. It pushed outward against the endless inward pull of gravity. When the fuel runs low, that outward push fades, and the core begins to contract. It shrinks, and it heats, and helium ash piles up at the centre, like cooling embers with no flame. Here is where the sun does something you might not expect. Ordinary gas resists being squeezed because it gets hotter, and hotter gas pushes back harder. That is how the sun has balanced itself for 4.5 billion years, but squeeze matter far enough and a different rule takes over. The electrons inside the core get packed so tightly that they run into a hard quantum wall. Two electrons cannot share the same state. They simply refuse, and that refusal itself becomes a pressure. This is called electron degeneracy pressure, and it is one of the strangest supports in nature. It does not come from heat. It comes from a rule of physics acting like a physical wall. You can pour more energy into this matter, you can raise its temperature, and the pressure barely notices. The core is now a degenerate core, held up not by warmth, but by a law. Take a moment with that idea before we go on. If you enjoy these slow walks through what the universe actually does, a like or a subscribe helps more than you would guess, and these scripts live on Spotify too. Now hold that picture, because it is the key to everything that follows. The sun's helium core keeps contracting under gravity. It keeps heating up, but its pressure is frozen in place by that quantum rule, unable to rise the way normal gas would. The temperature climbs past 20 million degrees Fahrenheit, then far beyond. And the whole time, the core cannot puff itself out to cope. It just gets hotter and hotter inside a box it cannot expand. The threshold it is climbing toward is a specific number. Helium will not fuse at the temperatures that burn hydrogen. It needs roughly 100 million Kelvin, about 10 times hotter than the sun's core is today. Helium nuclei carry twice the electric charge of hydrogen, so they repel each other far more fiercely, and only ferocious heat can slam them together. So the degenerate core waits, packed and silent, temperature rising, until it finally touches that 100 million mark. When it does, the helium lights. The reaction that ignites is called the triple alpha process, and it is a small miracle of timing. A helium-4 nucleus is also known as an alpha particle. Two of them can briefly stick together into beryllium-8, but that pairing is desperately unstable, gone in a fraction of a second. For fusion to proceed, a third helium nucleus has to arrive and join in during that vanishing instant. 3 helium-4 nuclei, caught together at the right moment, fuse into a single nucleus of carbon-12. That is the triple alpha process. It is how the universe builds carbon, the element you're largely made of, and it needs both crushing density and that 100 million degree heat to happen at all. In an ordinary star, this ignition would be gentle. Like the helium, the core warms, warm gas expands, expansion cools things back down, and the burning settles into a slow, steady simmer. That is the thermostat that has kept the sun so calm for so long. Heat causes expansion causes cooling, and the fire regulates itself. It is one of the quietest feedback loops in nature, but the degenerate core has no thermostat. Remember the rule: its pressure does not rise when you heat it. So when helium ignites, the fresh energy pours in, and the temperature leaps and nothing pushes back. The core cannot expand to cool itself. Instead, the extra heat only makes the triple alpha reaction faster, and a faster reaction dumps in even more heat, which makes it faster still. There is no brake, there is no valve. The fire feeds the fire. This is a thermal runaway, and it is savage. The burning rate does not creep upward, it explodes upward, doubling and redoubling as the temperature spikes. In the span of only a few hours, the sun's core will fuse helium at a rate almost beyond description. All of that violence unfolds in a pocket at the very centre of the star, in a window shorter than a single afternoon. And here is the number that should stop you cold. At the peak of this runaway, the core briefly pours out energy on the order of 100 million times the sun's entire current output. Not 100 million times brighter than a candle, 100 million times the whole sun. For those few hours, a pocket at the centre of the sun rivals the light of 100 billion stars. It briefly matches the power of the entire Milky Way galaxy, packed into a region smaller than a planet. You should hold that figure carefully, because it is a modelled estimate, not a thing anyone has ever watched happen. No telescope has ever caught a helium flash in the act. It is buried too deep, and it is over too fast. Everything we know about it comes from simulations, from the equations of stellar physics run forward on computers. The precise peak and the exact duration shift a little from one model to the next. But every model agrees on the essential shape. A runaway, a spike, a galaxy's worth of power lit in the dark for a few hours. Now comes the part that makes this the strangest moment in the whole story. You would think an event that fierce would tear the sun apart, or at the very least blaze out across the sky. It does neither. That titanic burst of energy is released deep inside the star, under layer upon layer of overlying gas hundreds of thousands of miles thick, and those layers swallow it whole. The energy does not blast outward. It gets absorbed, spread out, soaked up by the vast bulk of the star sitting on top of the core like a thick blanket over a struck match. So from the outside, almost nothing happens. The surface of the sun barely flickers. Its brightness, seen from a distance, changes so little that it would take careful measurement over a long time to notice any shift at all. An observer sitting nearby would see no flash. An observer light years away would see nothing whatsoever. The most powerful event in the sun's entire future life, an explosion that briefly rivals a galaxy, will happen in total secrecy. It makes no sound. It sends up no beacon. It is a fire sealed inside a wall of its own making. Sit with that paradox for a moment, because it is the heart of tonight's strangeness. Violence and silence folded into the same instant. 100 million suns of power, and not a single photon of it escaping to announce itself. The star that lights your whole sky will detonate at its core, and the sky will not so much as blink. What actually escapes is not light but change. The flash does its real work on the core itself. All that trapped energy finally does what heat has been unable to do for millions of years. It breaks the quantum stalemate. The temperature climbs so high that the electrons stop being degenerate. The packed lattice loosens. That hard quantum wall softens back into ordinary gas that once again expands when you heat it. The runaway, in other words, ends by destroying the very condition that made it a runaway. It does not end all at once. After the main flash, the core does not simply settle into calm, it convulses. A series of smaller sub-flashes follows, weaker echoes of the first, each one lifting a little more of the degeneracy, each one nudging the core closer to an ordinary state. You can think of it as a fire that flares hard, then coughs, then flares again more softly, then again softer still, spacing out its aftershocks as it burns off the last of that strange quantum stiffness. And then, at last, it steadies. The core expands into a normal gas once more. The thermostat comes back. Helium now burns in a calm, controlled, self-regulating way at the centre of the sun, with the same gentle feedback loop that once governed its hydrogen. Around that core, heat stirs the gas into slow overturning currents, a convective core, carrying energy outward the way a pot of water rolls as it warms. The star has crossed a threshold. It has stopped being a red giant climbing toward crisis and become a star with a new and steadier fuel, quietly turning helium into carbon and oxygen at its heart. This is the aftermath of the hidden fire. Not destruction, but a reset. The flash was never an ending, it was a passage. The sun spent tens of millions of years building toward those few violent hours, and it will spend the next long chapter of its life living in the calm those hours brought. For a while, a good long while by human reckoning, the sun burns helium as steadily as it once burned hydrogen, balanced and bright and unremarkable from the outside, giving no sign of the galaxy it briefly held in its chest. But this calm is borrowed, and it is short. Helium is a far poorer fuel than hydrogen, and there is far less of it. The sun will spend it quickly, and when the helium at the centre runs low, the same old pattern will return, sharper than before. The core will contract again. Shells of burning will layer themselves around it, hydrogen above helium, each shell flaring and pulsing in its turn. The star will grow unstable in a new way, swelling larger and looser than any red giant it has been before, its grip on its own outer layers weakening with every pulse. You can already feel where this is heading. The hidden fire proved something about the sun that will define its final acts. This is a star that stores its greatest violence deep inside, sealed away, and lets almost none of it show. The helium flash was the sun keeping a secret. What comes next is the sun letting go, not in a single blast, but in slow spreading exhalations of its own substance, breathed off into the cold. The core that survived the flash will one day be all that is left, an ember of carbon and oxygen, while everything around it drifts away. The wall of quantum pressure you met tonight will return too, in the very end, holding up the corpse the sun leaves behind. The same rule that made the flash a runaway will one day be the only thing keeping the sun's remains from collapsing entirely. That is the quiet symmetry of it. The stiffness that trapped the fire becomes the stiffness that outlives the fire. But that is a story for the long dark still ahead. For now, hold the picture of that sealed explosion, 100 million suns' power, a few short hours, a galaxy's worth of light, lit and swallowed in the same breath, deep beneath a surface that never flinches. It is the most dramatic thing the sun will ever do, and it is the thing no one will ever see. Consider what that fire in the core is actually trying to do. It is trying to build carbon, and carbon, strange as it sounds, is one of the hardest simple things in the whole universe to make. Start with the fuel. The core has run out of hydrogen. What is left, packed and glowing, is helium. Each helium nucleus carries 4 particles, 2 protons and 2 neutrons bound tight. To reach carbon, you need 12 of those particles in one nucleus, so the arithmetic looks almost trivial. Take 3 helium nuclei, 4 plus 4 plus 4, and you land exactly on 12. On paper, it is the easiest sum in the world. Nature refuses to let you do it in one clean motion. 3 separate nuclei almost never meet at the same instant. 2 might find each other, 3 arriving together in the same tiny pocket of space at the same fraction of a moment is so rare it may as well not happen. So the star cannot simply slam 3 helium nuclei into one. It has to build carbon in steps, and the steps are where the trouble begins. Here is the gap you have to cross. When 2 helium nuclei fuse, they make a nucleus of 8 particles. It is called beryllium-8, and beryllium-8 barely wants to exist at all. There is no stable nucleus anywhere with exactly 5 particles in it, and none with exactly 8 either. The ladder of ordinary matter is missing 2 of its rungs, right at the place you need to put your feet. You cannot bridge helium to carbon directly, because the natural stepping stone crumbles. Picture that stepping stone honestly. 2 helium nuclei collide and stick, and for the smallest sliver of time you have beryllium-8. Then it falls apart again, back into the 2 nuclei it came from in a tiny fraction of a second. It is a stone that shatters almost the instant your foot lands on it. You do not get to stand there and rest. You do not get to wait for help to arrive. The window is open, and then it is gone. Over and over, everywhere in the core at once. So how does anything cross? This is where the conditions inside the star do the impossible-looking work. The helium core is not a gentle place. It has contracted under its own weight until it reaches about 100 million Kelvin. It is crushed to a density far beyond anything you could hold or imagine. In that furnace, helium nuclei are not drifting. They are hurled at each other constantly, at colossal speed, in numbers past counting. That density is the whole trick. Beryllium-8 lives for only a flicker, but in a place this crowded, a flicker is enough. Before that fragile nucleus can fall apart, sometimes, just sometimes, a 3rd helium nucleus slams into it. If the timing lands inside that vanishing window, the 3 lock together. 8 particles plus 4, 12. A nucleus of carbon-12 is born, and this one is stable. It stays. The stepping stone caught a second foot before it could crumble, and the crossing was made. Hold the odds in your mind for a moment, because they are the strange heart of this. For any single beryllium-8 nucleus, the chance that a third helium arrives in time is minuscule. Almost every one of them simply falls back apart, unused, having built nothing. The reaction should barely happen. And yet the core is fusing helium into carbon at a serious rate. The reason is pure quantity. There are so many nuclei, colliding so many times each second, that even an outcome this unlikely still happens again and again. You lose nearly every attempt. You make so many attempts that the rare wins pile into something real. This is the pathway with a name. Astronomers call it the triple alpha process, because a helium nucleus is also known as an alpha particle, and 3 of them are joined to make each carbon atom. 2 fuse into fleeting beryllium-8. A third catches it before it dies. That is the entire recipe, run trillions upon trillions of times deep inside a star. Now notice how sensitive the whole thing is. The triple alpha process depends on 2 conditions holding at once: temperature and density, and it depends on them steeply. Cool the core a little, and the nuclei move slower, and fewer third catches land inside the window, and the carbon building nearly stops. Heat it a little, and the collisions come faster and harder, and the rate does not just rise, it climbs almost violently. The reaction responds to temperature far more sharply than ordinary burning does. A small nudge upward in heat becomes a large surge in fusion. That steepness is exactly why helium fusion does not switch on gently. It ignites. Below about 100 million Kelvin, almost nothing happens because the third catch is too rare to matter. Cross that threshold, and the triple alpha process suddenly lights, all at once, across the core. In a normal star, this is dramatic but controlled. The gas heats, expands, cools itself slightly, and settles into a steady burn. Rising temperature pushes the gas apart, which eases the temperature back down. The star holds its own hand, but the future sun will not light its helium in a normal gas. By the time this moment arrives, the core has been squeezed into a peculiar state. It is held up not by heat, but by a quantum rule, the sheer refusal of its electrons to be packed any tighter. In that condition, the usual safety valve is gone. When the triple alpha process ignites, the core heats up, and the fusion rate leaps with it, and yet the core does not expand to cool itself. The pressure barely notices the temperature, so the heat has nowhere to go, and more heat means more fusion, and more fusion means still more heat. The reaction feeds itself and accelerates, with no break to catch it. This is the runaway hidden inside the star, and the reason it matters to you sitting here is closer than any of it sounds. Every carbon atom you're made of was built this way. The carbon in your bones, in the proteins holding your body together, in every strand of you, was forged by 3 helium nuclei caught together through that flickering beryllium stepping stone in the crushing core of some star that lived and died before the sun was born. There is no other place carbon comes from. It is not made in the quiet of space. It is made only in this improbable 3-body catch at 100 million degrees against odds that should have failed. The world is full of it because stars, given enough collisions and enough time, turn the unlikely into the ordinary. That same reaction, the one that seeded the carbon in your hands, is the reaction about to fire inside the sun. When its core finally reaches that threshold, the triple alpha process will ignite in matter that cannot cool itself, and the burning will surge far past anything gentle, a buried flash of fusion sealed so deep that nothing on the surface will show. When that hidden runaway finally settles, the sun will begin to shed itself layer by layer into the dark around it. When that hidden runaway finally settles, the sun will begin to shed itself layer by layer into the dark around it. When that hidden runaway finally settles, the sun will begin to shed itself layer by layer into the dark around it. By then it has become something with a long and awkward name. Astronomers call it an asymptotic giant branch star. You can set the name aside. What matters is the shape of it. At the very centre sits a dead core of carbon and oxygen. That core no longer burns. It is inert, packed tight, holding its heat but making no new energy of its own. Around that silent core, the sun keeps two fires going. One is a thin shell of hydrogen, fusing where it meets the cooler gas above. Below it, closer in, is a shell of helium. These two shells take turns. Picture two rings of flame stacked around a cold stone at the middle. That is the sun in this stage, a dead heart wrapped in burning skins. The turns those shells take are not gentle. Every so often the helium shell chokes on its own ash. Pressure climbs, then it ignites in a sudden burst. Astronomers call these bursts thermal pulses. Each one is a shudder that runs up through the whole star. The outer layers heave. The surface swells and cools, then draws back, then swells again. The sun in this phase is not steady at all. It breathes. It convulses on a slow clock, over thousands of years, a great unstable thing trying to find a balance it can no longer keep. Before we go further into the shedding, one small ask. If this slow story is holding you, a like or a subscribe helps more people find these quiet nights, and you can find Deep Space Drift on Spotify too. That is all. Now let the sun keep coming apart. These pulses do something important. They loosen the star's grip on its own outer body. A red giant is enormous and diffuse. Its outer layers are held on weakly, far from the gravity of the shrunken core. And with every thermal pulse, more of that outer gas is pushed up and out, a little further each time, until it stops coming back down. This is where the real shedding begins. At the end of the asymptotic giant branch phase, a star enters what astronomers call a superwind. The name fits. It is a wind of gas pouring off the star, but on a scale that is hard to hold in the mind. During this stage, a dying star like the Sun will throw off somewhere between 20 and 80% of its entire mass. Nearly the whole hydrogen-rich envelope, the vast puffed-out body of the giant, blows away into space, and it happens quickly, at least by the standards of a star. What took billions of years to build is loosened and cast off in a comparatively short time. Think about what that means for the Sun's material. Most of what you would call the Sun, the gas you see as light, does not collapse and does not burn away to nothing. It simply leaves, drifts outward in every direction, a slow, expanding tide of the star's own substance, thinning as it goes. But what actually pushes it? A wind needs something to blow on. And here the answer is one of the stranger turns in a star's whole life. The answer is dust. Actual soot. To see how, you have to look at the chemistry of the outer layers. Deep inside, the thermal pulses have been dredging fresh carbon up from the core region and mixing it toward the surface. Over time, carbon builds up in the star's outer gas, and at some point it crosses a line. Carbon becomes more abundant than oxygen out there. That balance matters more than it sounds. Once carbon outnumbers oxygen, the cooling gas can begin to condense carbon straight out of itself into tiny solid grains. Specks of carbon-rich dust form in the outer atmosphere of the star, the way soot forms in a plume of smoke. Now the star has something to push. Light carries pressure. It is faint pressure, far too weak for you to feel, but a star pours out an ocean of light. That radiation streams outward and strikes the newly formed dust grains. It pushes on them, and the grains, dragged outward, collide with the gas around them and haul it along too. Dust catches the light, gas catches the dust, and the whole envelope is swept off into space. That is the engine of the superwind. A star losing its skin because it made soot, and the soot caught the starlight, and the starlight blew it away. For a long stretch, none of this glows the way you might expect. The ejected gas is cool. It expands quietly outward, invisible, a widening shell of ordinary matter carrying no light of its own. It could pass in front of nothing, and you would never know it was there. Then two things change at once, and the darkness turns to light. The first change is out in the shell. As the ejected envelope keeps expanding, it grows thinner and thinner. It turns transparent. Light that once would have been trapped inside it can now pass straight through. The second change is at the centre. As the outer layers peel away, they uncover what was hidden beneath them all along. The naked core. That small, blazing, exposed heart of the star, far hotter than the sun's surface is today. And a body that hot does not shine in soft yellow light. It floods space with ultraviolet, the same invisible energy that burns your skin on a summer afternoon, but poured out at a ferocious level. That ultraviolet light now reaches the expanding shell and pours into it. And it does to the gas what a current does to a neon tube. It ionizes it. It strips electrons from the atoms and pumps energy into them, and the gas answers by glowing. The whole vast shroud lights up from within. What was an invisible cloud becomes a luminous ring, a glowing bubble of the star's own former body, lit by the fierce blue-white core it left behind. This glowing shell has a name, and it is one of the most misleading names in all of astronomy. It is called a planetary nebula. It has nothing whatsoever to do with planets. No planet forms in it. No planet is destroyed to make it. The name is a leftover from centuries ago, when early observers looked through small telescopes and saw a soft, round, pale disk. It reminded them of a planet, a little rounded orb rather than a pinpoint star. The name stuck, wrong as it was, and we still use it today. So when you hear planetary nebula, translate it in your mind. It means a dying star's cast-off skin, glowing. These objects are, by the standards of the cosmos, almost fleeting. A planetary nebula is visible for only around 10,000 to 50,000 years. After that, the glowing gas keeps expanding until it thins out too far, spreads into the space between the stars and fades from view. The light goes out. The material does not vanish. It simply mixes into the great reservoir of gas that drifts through the galaxy, ready one day to gather into something new. But the bright shell itself, the visible ring, lasts only that brief window. Set against a star's 10 billion years of a life, 10,000 years is the last soft exhale. You do not have to imagine what this looks like. The sky is full of them right now, other suns caught in the exact act the sun will one day perform, and you can look at them as previews of your own star's distant future. One of the closest hangs about 655 light-years away. Its catalogue name is NGC 7293, but almost no one calls it that. People call it the Helix Nebula, and many call it the Eye of God, because that is exactly what it looks like. There is a bright inner ring glowing like a pupil. Around it spread fainter filaments, drawn out like the fibres of an iris. It stares out of the dark, wide and calm and enormous. That single glowing eye is nearly 3 light-years across, and it was made by a star much like the Sun. By the measurements we have, it is only around 10,600 years old. You're looking at a very recent death, a shell freshly lit, a star that finished shedding its skin about as long ago as human civilization is old. Another sits farther out, about 3,300 light-years away, in the constellation Draco. This one is called the Cat's Eye Nebula, NGC 6543, and it is stranger still. Instead of a single clean shell, it shows at least 11 concentric rings, nested inside one another like the layers of a Russian doll. Each ring is the edge of a separate bubble of gas, seen glowing in projection, one inside the next, like nested globes of thin glass. Astronomers think each of those shells was flung off in a separate convulsion of the dying star, a pulse of mass ejected roughly every 1,500 years, a slow, repeating heartbeat of loss. And here is the detail that stops you. Each one of those faint rings holds about as much matter as every planet in the solar system combined. Whole worlds worth of gas in a single glowing thread. We do not fully understand why the cat's eye is so patterned. The neat rings and the twists at its centre are not completely explained. One leading idea is that the pulses came at regular intervals. Another suspects a hidden companion star, tugging on the dying giant and shaping what it throws off. Both remain suggestions, not settled facts. It is one of those honest gaps in the science, a beautiful object we can photograph in detail and still cannot fully account for. Hold on to why these two nebulae matter for you. They are not curiosities from some other kind of star. They are portraits of the sun's own future, painted early. In several billion years, when the sun sheds its envelope and its exposed core lights the escaping gas, the solar system will become one of these. From a great distance, some future observer, if any exist, would see a glowing shell where the sun used to be, an expanding ring of solar material, lit from inside by a small, savagely hot pointer light. The gas of that ring would be the very stuff the sun is made of now, the atoms that make its light today, drifting outward and shining one last time. Somewhere in that ring, in a sense, would be us. The material of the inner planets, whatever the red giant left behind, mingled into the outflow, the carbon that formed as soot and rode the starlight away, all of it spreading into a bright, brief, beautiful shell that a distant astronomer might catalogue with a number and a nickname, never knowing they were looking at a solar system's grave. And that shell, like all the others, would not last. 10,000 years, perhaps 50,000 at the outside. Then it thins and spreads and dims, and the light of the sun's final glow leaks away into the dark between the stars. The gas keeps going, carried on nothing, joining the slow rivers of matter that wander the galaxy. Some far future star, some far future world, might be built in part from what was once the sun. That is not an ending so much as a scattering. The sun does not die into nothing. It comes apart and gives itself back. But while all of this plays out in the shell, while the gas glows and expands and fades, something is being uncovered at the middle of it. The whole point of the shedding in the end is what it reveals. Layer after layer has blown away. The burning shells have gone quiet. The vast body of the giant has been carried off on the wind, and what is left is small and dense and impossibly hot, waiting at the centre of the glow. Raw narration only. No local file system write tool is available in this session, so I'm delivering the insert text directly below. It is ready to splice before the anchor sentence. There are places in the sky where you can already see how this ends, not in theory and not in a simulation. In real light, gathered by real telescopes from stars that have already done what the sun has yet to do. They're called planetary nebulae, and two of them are worth holding in your mind tonight, because between them they sketch the whole shape of the sun's future. The first sits about 655 light-years away, close as these things go. Its catalogue name is NGC 7293. Most people know it by a gentler nickname, the Eye of God, though astronomers usually call it the Helix Nebula. That distance is not a rough guess. It comes from the Gaia spacecraft, which measured the tiny shift of the central star against the background sky and pinned the number down with real precision. When you look at the helix, you're looking at light that left it around the fall of the Roman Empire, and it has been crossing empty space toward you ever since. The nebula is enormous and yet delicate. It spans roughly 2.87 light-years from one edge to the other. To cross it at the speed of light would take you the better part of 3 years, and it truly does look like an eye. There is a bright inner ring, glowing like a pupil, a dense band of gas lit from within. Around that pupil lies a fainter structure, softer and more thread-like, spreading outward in pale filaments like the fibres of an iris. Radial streamers point back toward the centre, thousands of them, each one a comet-shaped knot of gas the size of the solar system. What makes the helix so quietly astonishing is its age. This whole glowing eye is only about 10,600 years old. In cosmic terms, that is nothing. 10,000 years ago, human beings were painting on cave walls and learning to farm. In that same span of time, an ordinary star very much like the Sun finished dying and lit up this shroud of its own gas. The star that made it was a sun, not a giant, not a monster, a yellow middleweight star that ran out of fuel, swelled, and breathed off its outer layers into the dark. What you see is the aftermath, still expanding, still glowing, still young. Now hold that image and travel farther out, about 3,300 light-years, into the constellation Draco, the dragon that coils around the northern pole. There you will find the second portrait. Its catalogue name is NGC 6543, and it is better known as the Cat's Eye Nebula. If the helix is calm and eye-like, the Cat's Eye is intricate almost beyond belief. When the Hubble Space Telescope turned toward it, it revealed something no one had expected. Around the bright central knot lie at least 11 concentric rings, nested one inside the other like a set of Russian dolls made of light. Those rings are not flat circles painted on the sky. Each one is the edge of a complete spherical bubble of gas, a shell blown out from the star in every direction at once. You see a ring rather than a sphere only because you're looking through the thin glowing rim where the bubble is deepest along your line of sight. Picture 11 soap bubbles, one inside the next, each frozen at a different size. Look through them from outside, and every bubble shows itself as a bright circle. That is the Cat's Eye. 11 or more nested globes of gas, each marking a separate breath the dying star once took. And that word, breath, is the key to how these rings were made. The star at the centre did not shed its skin in one smooth exhale. It convulsed. It ejected mass in slow repeating pulses, and the best estimates space those pulses roughly every 500 years. Every 15 centuries or so, the star heaved off another shell of gas, then paused, then heaved again. 15 centuries of quiet, then a pulse, 15 more, then another. The rings you see are the record of that slow, patient heartbeat, written across thousands of years. The amounts involved are hard to hold in your head. Each of those shells is thought to carry as much mass as every planet in the solar system combined. Take Jupiter, Saturn, Neptune, Uranus, the Earth, all of them. Roll their entire weight into a single glowing bubble of gas, and that is one ring. Then do it again for the next ring, and the next 11 times over. The star was pouring away planet loads of its own substance, again and again, until almost nothing of its outer body remained. Here is the part worth being honest about. No one is entirely sure why the Cat's Eye looks the way it does. The full ring pattern has never been completely explained. Steady pulses every 1,500 years account for the regular spacing of the shells, and that is one leading idea. But the nebula has other features, jets and knots, and a strange symmetry that simple pulsing does not easily produce. So many astronomers suspect the central star is not alone. They think there may be a hidden companion, a second star locked in a close orbit, unseen in the glare, its gravity stirring the outflowing gas into these elaborate shapes. A pulsing single star or a buried binary quietly shaping the wreckage. Both ideas are on the table, neither is one. It remains one of the open questions in the sky, a puzzle still waiting on better data. You do not need to resolve that puzzle to feel the weight of what these two nebulae mean, because neither of them is a special case. Neither is a freak of nature. The helix was made by a star like the Sun. The Cat's Eye was made by a star like the Sun. What you're seeing, in both, is the ordinary fate of an ordinary star, caught at the one brief moment when it becomes visible from light years away. Think about that when you look at them. The helix is not a curiosity in someone else's sky. It is a preview of your own. Several billion years from now, when the Sun has finished swelling and shuddering and casting off its outer layers, it it will build a shroud of glowing gas exactly like these. Somewhere out there, on some world circling another star, an observer with a good telescope might one day turn toward the faint spot where the sun used to be and see a ring, a soft, glowing eye, a set of nested bubbles expanding into the dark. They would give it a catalogue number. They would measure its distance and its width and its age, and they would never guess that it had once been a warm yellow star with a small blue planet in its third orbit, where someone long ago lay awake at night wondering how it would all end. Every planetary nebula in the galaxy is a portrait like that, a corpse portrait of some other sun, standing in for the story of our own. The glowing eye of the helix, the nested rings of the cat's eye, each is a snapshot of the same slow event, frozen at a slightly different stage. Gas flung outward, light pouring through it, and a shroud, thin and luminous, drifting away from something small and hot at the very heart of it. Because that is the last thing these portraits show you if you look past the glowing gas to the point at the centre. In every one of them, ringed by all that expanding light, sits a single tiny star, the source of the ultraviolet glow that lights the whole nebula up. The stripped, exposed core of the star that made it. In the helix, in the cat's eye, in every glowing eye across the galaxy, the shells are only the outer layers thrown away. The real story is that pinpoint at the middle, blazing hot and impossibly small, all that remains after everything else has been shed. What remains at the very centre, once that glowing shroud has drifted away, is a single naked ember no larger than the Earth. Word count, approximately 1,490 words. Pre-flight, self-check on this insert, word budget 1 × 600, pass 1 × 90, opens as natural continuation, ends flush into anchor. Pass, named objects with numbers. NGC 7293, 655L, 2.87 Dells, 10,600 NGC 6543, 3,300 Elysian, Draco, 11 plus strings, 1,500 Riddlewire pulses. Pass, no dashes, ASCII only. Pass, no canonical scaffold phrases, no timestamps, no headers. Pass, contested ring mechanism flagged. Pulses versus binary, not settled. Pass, imperial, allowed units, light years only. Pass, short sentence sleep cadence, second person. Pass. Note, I could not write to Claude, agents, DSD scripts, because this session has no local file write tool, only MCP connectors are available. If you want it saved, I can create the file in Google Drive instead, or you can paste the text above into the target path. What remains at the very centre, once that glowing shroud has drifted away, is a single, naked ember no larger than the Earth. What remains at the very centre, once that glowing shroud has drifted away, is a single naked ember no larger than the Earth. This is the Sun. Not the wide golden disk you know, but everything left of it after the outer layers are gone. The whole hot heart of the star has been laid bare, and it has been crushed down into something almost impossible to picture. Think about the numbers for a moment. The Sun today holds 1 solar mass. By this point it has shed most of its body to space. Roughly half of it remains, somewhere around 0.5 to 0.6 solar masses. That leftover core is packed into a ball about the size of our planet. Half a sun, folded into a world you could fit inside Earth's own outline. That is what a white dwarf is. Before we sink into what happens next, one small thing. If these slow, strange endings are the kind of story you want to fall asleep to, a like or a follow helps more people find them, and the channel lives on Spotify too, that is all. Now, let the star pull us back in. What holds this ember up is worth pausing on. There is no fire left inside it, no fusion, no burning, no engine. An ordinary star stays swollen because heat pushes outward against gravity. Take the heat away, and gravity should win. It should keep squeezing. Yet the white dwarf does not collapse. Something stops it. That something is electron degeneracy pressure. It comes from a hard rule buried in the quantum world. Two electrons cannot share the same state. Pack them close enough, and they simply refuse to be pushed any closer. It is not warmth holding the star open. It is a law, a rule of reality acting like a wall of stone. You press, and it presses back, cold and absolute. That refusal is why the matter inside is so dense. Here is where the numbers stop feeling real. A white dwarf is roughly 200,000 times denser than the Earth beneath you. Not twice, not 100 times, 200,000. The atoms have been stripped and crushed until the nuclei swim in a sea of shared electrons. Ordinary matter no longer exists in there. It has become something else entirely. Let me hand you the weight of it. Imagine a single teaspoon. A small, everyday spoon, the kind you stir with. Fill it with white dwarf material. That one spoonful would weigh about 5.5 tons. That is the weight of a full-grown elephant balanced on the end of a spoon. You could not lift it. You could not even move it. The whole planet it sat on would feel it. Hold that picture as we look at the ember itself. When the white dwarf is first exposed, it is not dim. It is not the faint red thing it will one day become. It is blazing. Its surface sits somewhere near 20,000 to 30,000 Kelvin. That is far hotter and far whiter than the sun you see in the sky today. The core of the sun has been dragged into the open, and it shines with its old buried heat. But that heat is all it has. Understand this clearly. There is no fuel. Nothing is being made. Nothing is being burned. Every scrap of warmth pouring off that surface is leftover heat, and once it is gone, it is gone. The white dwarf is a coal pulled from a fire that has already died. It glows only because it has not yet finished cooling, and the cooling is slow beyond anything you have ever measured against a human life. How slow, you will see in a moment. First, something happens inside the ember that almost nobody expects. As the white dwarf cools, its interior begins to change state. The carbon and oxygen packed into its heart do not stay a fluid forever. They freeze, not into ice, but into a solid. The atoms lock together into an ordered pattern, a rigid lattice, row on row, the way a liquid turns to crystal. This was long only a theory. Back in 1968, physicists predicted that white dwarfs should crystallize as they cooled. It was an elegant idea, and for half a century it stayed just that, an idea on paper. Nobody had seen it. Nobody could point to a single star and say, "There, that one is turning solid inside." Then the proof arrived. In January of 2019, an international team led by Dr. Pierre-Emmanuel Tremblay at the University of Warwick published their findings in the journal Nature. They had used the European Space Agency's Gaia satellite, which measured huge numbers of white dwarfs with extraordinary care, and in that flood of data they found the fingerprint, the first direct evidence that white dwarfs really do freeze from the inside out. A 51-year-old prediction finally caught in the act. The freezing happens at a staggering heat. The carbon and oxygen crystallize when the interior sits around 18 million degrees Fahrenheit. Let that sit with you. The star is so hot inside that its temperature is measured in the millions, and yet it is freezing. Cold and hot have swapped their ordinary meanings. It is not the chill you feel on a winter night. It is a phase change, matter settling into order because it has finally cooled just enough to lock in place. And the freezing does something curious to the clock. When the interior crystallizes, it releases heat. That released warmth flows back into the star and slows its cooling even further. The white dwarf lingers. It holds its temperature longer than it otherwise would. So long, in fact, that it fools us. The Gaia measurements showed this plainly. Some white dwarfs appear up to 2 billion years younger than they truly are, simply because crystallization stalled their cooling and kept them warm. The team found a whole population of these stars, caught in the transition, their cooling effectively frozen in place for more than 8 billion years. Picture that. a star sitting on a shelf of time, holding still while more than half the age of the universe slides past outside it. This is why the white dwarf earned a nickname. When carbon locks into an ordered lattice, it forms the same structure found in a cut diamond. So people began calling these cooling cores diamond stars. It is a poetic phrase, and for once the poetry is close to the physics. The sun's final form is quite literally a crystallizing gem the size of a planet. An Earth-sized jewel, freezing solid in the dark, one layer at a time. Now we come to the cooling itself, and the timescale that puts every human number to shame. A white dwarf has nothing left but its stored heat to give away. It radiates that heat into empty space, slowly, patiently, forever. And forever is barely an exaggeration. Here is the figure that should stop you. Take a white dwarf glowing at 20,000 Kelvin. Let it cool. Wait the entire age of the universe, all 13.8 billion years that have passed since the beginning of everything. In all that time, that star would cool by only about 40 Kelvin. 40, not 40,000. 40. The whole span of cosmic history, every galaxy that ever formed, every star that lived and died, and the ember has barely dimmed. Sit with what that means. No white dwarf anywhere in the universe has finished cooling. Not one. There has not been enough time. The universe is not old enough. Every white dwarf you could point a telescope at is still warm, still glowing, still bleeding away heat it gathered before the Earth existed. They are all only partway through. Every single one. This is where you can let the pace of it carry you down. There is nothing urgent here, nothing you need to hold. The white dwarf is in no hurry, and neither are you. It simply glows, and fades, and glows, over stretches of time so long they lose all meaning. You could sleep 1,000 years and it would not notice. You could sleep 1,000,000, and its light would look the same. The colours will shift, though, across those unimaginable ages. The ember begins white-hot, brilliant and sharp. Then, over billions and billions of years, it slides down through the shades. White softens toward yellow, yellow deepens toward orange, orange sinks toward a dull, sullen red. And still it goes on, cooling by fractions, dimming by degrees, long after any planet around it has gone silent and cold. There is an endpoint to this, a true, final state that the whole long story has been walking toward. When a white dwarf at last radiates away every trace of its heat, when it stops glowing altogether and goes fully dark, it becomes something with a name and no examples. A black dwarf, a dead star, cold through and through, giving off no light at all. Just a crystalline mass drifting in the black, indistinguishable from the emptiness around it. But here is the strange truth about the black dwarf. No one has ever seen one, not because they are hidden, and not because they are hard to find, because none exists. The time required for a white dwarf to cool all the way down is calculated to be far, far longer than the current age of the universe. The cosmos is 13.8 billion years old, and that is nowhere near enough. Every white dwarf ever born is still cooling. The black dwarf is a prediction, an extrapolation, a place on the timeline we can point to but never visit. It waits in a future so distant it may as well be a rumour. So this is what the sun becomes. Trace the whole path once more gently before you drift. It never explodes. It swells and sheds its skin and lays its core bare. That core is an Earth-sized ember of half a sun, held open by a quantum rule, dense enough to weigh an elephant on a spoon. It freezes from the inside into a diamond-like lattice, a process we only proved was real in 2019, confirming a guess made back in 1968. And then it cools, slowly, so slowly that the age of the universe buys it only 40 degrees. That is what it will actually do instead of anything loud. There is a quiet grandeur in it, if you let yourself feel it. We are trained to expect endings that are violent. Fire, noise, a final flash. The sun offers none of that. Its close is patient beyond reckoning. It is a light that dims so gradually that no clock we own can measure the change. It will still be glowing, faintly, after the last bright stars have burned out across the whole sky. It will outlast almost everything. Picture it there at the end. A single frozen gem the size of a world, resting in a darkness with nothing left to burn, no fuel, no fire, no sound. Only the slow surrender of the last warmth it will ever hold, given up to the cold one whisper at a time. That is the sun's true grave. Not a wound in the sky, but a jewel going quietly dim over an ocean of years. No local script writing tool, Write Edit, is available in this session, and the target path, Claude Agents DSD scripts, is on the local file system, which I cannot reach from here. I could not save the file. Below is the finished insert lay as raw narration, ready to be pasted into the file. Before anyone gave that corpse a name, one of them was already sitting in a telescope unnoticed. The night was the 31st January 1783. William Herschel, the man who had found the planet Uranus 2 years earlier, was sweeping the sky in the constellation Eridanus. He logged a faint point of light beside a brighter star, a small companion in a system now called 40 Eridani. He wrote it down. He moved on. He had no idea what he had just seen. Nobody did. It would take almost a century and a half before science understood that this dim little speck was the first white dwarf ever observed by human eyes, the burnt-down ember of a star very much like our own. That is how these objects came to us, not announced, not predicted, just quietly present, waiting in the data for the rest of physics to catch up. And the story of how it caught up is one of the most patient detective cases in all of astronomy. Keep that in mind as the sun's own future takes shape. Every fact you now hold about its ending was assembled slowly, clue by clue, by people who mostly did not live to see the answer. The next clue arrived in 1844, and it came not from a faint star but from the brightest one in the entire sky, Sirius. You have looked at it yourself on a winter night, a hard blue-white spark low in the south. The German astronomer Friedrich Bessel had been measuring its position for years, tracking it against the fixed background of the sky. And Sirius would not hold still. It was weaving. Not wildly, just a slow, gentle wobble, a side-to-side drift over decades. A single star moving through space travels in a straight line. Sirius did not. Something was pulling on it. Bessel could see nothing there, but he trusted the arithmetic more than his eyes. He worked out that Sirius must have a companion, an unseen partner, and the two of them were swinging around their shared centre of gravity like a hammer thrower turning slowly on the spot. The pull needed to bend the path of the brightest star in the sky was not small, so the hidden object had to be heavy, roughly as heavy as the sun. Yet it gave off no light he could detect. He called it a dark companion. He had, in effect, weighed a ghost. Bessel died in 1846, 2 years after the prediction, without ever seeing the thing he had proven must exist. For 18 years it stayed hidden. The hunt needed better glass. It got it in a workshop in Cambridgeport, Massachusetts, where a father and son built telescope lenses by hand. In January of 1862, Alvan Graham Clark was testing a brand new lens, a refractor 18.5 inches across, at that moment the largest in the world. To test a great lens, you point it at a demanding target, and few targets are more demanding than Sirius, because its glare drowns everything nearby. Clark aimed the new instrument at it, and there, tucked into the flood of light, he caught a faint speck, a dim point almost lost in the blaze, like a single candle held up beside a searchlight. It sat exactly where Bessel had said it would. The dark companion was dark no longer. Clark had become the first person to see Sirius B, the star that had been tugging on Sirius for 18 years of careful mathematics. His first thought was not triumph. It was worry that his beautiful new lens had a flaw, that the speck was a defect in the glass. He swung the telescope to other stars. The speck stayed with Sirius. It was real. A telescope maker, testing his product, had just closed a case that a dead astronomer had opened almost 2 decades before. Now they could see it. They still had no idea what it was. That took another paradox, and it took until 1915. At the Mount Wilson Observatory in California, an astronomer named Walter Adams turned his attention to the faint companion and did something new. He spread its light into a spectrum, the rainbow smear that carries a star's fingerprints. He wanted to read its temperature, and the answer made no sense. Sirius B was hot. Not merely warm, but ferociously hot, running nearly 3 times hotter than the blazing Sirius A right beside it, a star that hot should pour out light. This one was pitifully faint, dimmer by far than its brilliant neighbour. Here were 2 numbers that refused to sit together in the same object. Blazing heat and almost no brightness. In astronomy, those 2 facts pull in opposite directions, and when they contradict each other, only one explanation survives. A hot object that gives off very little light must be very, very small. That is the only way out. If every square foot of a surface is fiercely hot, and yet the whole star still looks feeble, then there can hardly be any surface at all. Sirius B had to be tiny. Not tiny like a small star. Tiny like a planet. Astronomers were being forced, against every instinct they had, to picture a star crushed down to roughly the size of the Earth, still carrying about the mass of the Sun and glowing white hot as it did so. Small but blazing. The 2 words that should not belong together, describing one real object hanging in the sky. Sit with how strange that was for the people who first met it. Nothing in ordinary experience prepares you for it. Pack the entire Sun into a ball the width of the Earth, and a single teaspoon of the stuff would weigh about 5.5 tons. 1 spoonful, the weight of an elephant. That number came later, once the density was understood, and when it did arrive it read less like astronomy and more like a riddle. But in 1915 the community had only the paradox itself, a star that was heavy as the Sun, hot as a furnace, and no bigger than a planet. They had the measurement. They had no physics that allowed it. The name came before the explanation, as names often do. In 1922, an astronomer named Willem Luyten was writing about this odd little class of stars, these dim, hot, dense oddities, and he reached for a phrase to hold them together. He called them white dwarfs, white for the colour of their fierce heat, dwarf for their impossibly small size. The label stuck, and it is the one you still use today, though at the moment he coined it nobody could yet say why such a star could exist at all. The word was ready years before the mechanism was, and that is the quiet lesson buried in this whole 100-year chase. First came a speck nobody understood in 1783, then a wobble and a bold prediction in 1844, then a candle spotted beside a searchlight in 1862, then an impossible spectrum in 1915, then a name in 1922. Each step arrived alone, often separated by decades, handed from one lifetime to the next. Herschel never learned what he had logged. Bessel never saw what he had weighed. The full physics that finally made sense of the density, the crush of matter squeezed until the ordinary rules of atoms give way, would not be worked out until the years after Luyten had already named them. You are looking at that same kind of star when you look ahead to the Sun. This is what it becomes. Not a bomb, not a flash, but one of these small, dense, patient embers, the same family clock caught hiding in the glare of Sirius. Everything strange about Sirius B is a preview of the Sun's own last shape. Heavy beyond reason, hot to begin with, no bigger than the world you stand on, and with nothing left inside to burn, only heat to slowly leak away into the cold. That is what the detectives were really uncovering, though it took them a century to say it plainly. A white dwarf does not do anything dramatic. It does not detonate. It sits, and it cools, and it fades, over spans of time that dwarf the age of the universe itself. The whole long chase, from Herschel's speck to Luyten's name, was science slowly learning to recognise a very particular kind of quiet, an object whose entire future is to grow colder and dimmer, and to keep doing so long after everything around it has gone dark. Word count, approximately 1590. Pre-flight, self-check. Opens as a smooth continuation, not a recap. Ends so the anchor sentence follows naturally. ASCII only. 0 dashes. No timestamps or headers. Imperial units. Feet, tons, elephant weight. Short calm sentences, one idea each. All facts traced to the brief. Herschel Jan 31 1783. Bessel 1844 wobble. Clark 1862 18.5-inch refractor Cambridgeport. Adams 1915 Mount Wilson. Thurix hotter yet fainter. Luyten 1922. Teaspoon tummer 5.5 tons. No canonical scaffold phrases used. One caveat. I did not describe the density mechanism as fully settled, keeping to the brief. Note. Please save the text above to Stotclaude Agents DSD scripts first, White Dwarfs insert MDUS or your chosen slug. I lacked a file system tool to write it here, and so the sun's true ending is not a bang at all, but a slow freezing into the dark that will outlast the stars themselves. And so the sun's true ending is not a bang at all, but a slow freezing into the dark that will outlast the stars themselves. There is no detonation waiting in its future. There is no final flash. It carries one solar mass, and a supernova demands roughly 8, so the trigger simply is not there. It cannot forge an iron core to collapse. It can fuse only as far as carbon and oxygen, and then the fire runs out of anything left to burn. What remains is not violence. What remains is settling. Hold that in your mind for a moment. The ending you were told to fear was always too loud for the star that will actually die. The sun is a lightweight, gentle by the standards of the cosmos, and its death is written in that gentleness. Picture the whole arc now, laid out softly in the dark. First, the slow brightening. A star growing warmer by degrees across billions of years, until Earth's oceans lift away as vapour and the surface goes quiet. Then the swelling, the red giant reaching outward, dim and vast, filling more of the sky each million years until it may stretch to nearly 250 times its present size. And somewhere deep inside, sealed away where no one could ever see it, the helium flash, a fire briefly fierce enough to rival a galaxy, absorbed so completely by the layers above that the surface barely flickers. The most violent moment of the sun's life will be a secret it keeps to itself. Then the shedding. The outer envelope, most of the star, blown gently off into space on a slow wind, drifting outward as a glowing shroud lit from within by the hot exposed core. That shroud is a planetary nebula, a soft ring of light like the ones we already photograph across the galaxy, each one a portrait of what the sun will one day become. The helix, the one they call the Eye of God, is such a shell around a star much like ours. When you look at it, you are looking at a rehearsal. You are seeing the sun's future written on another star's ending, and at the centre of that fading ring the last thing left, an ember roughly the size of the Earth, holding half the sun's mass in a sphere you could fit between here and the horizon. A white dwarf, its material so dense that a single teaspoon would weigh as much as an elephant, around 5.5 tons balanced on a spoon. It has nothing left to fuse. It only cools, and it cools so slowly that the numbers stop feeling real. A white dwarf drops just a few dozen degrees across the entire age of the universe so far. Not one has ever finished cooling. Not one anywhere. As it cools, something quietly beautiful happens inside. The carbon and oxygen begin to lock into an ordered lattice, freezing the way water freezes into ice, only into a structure much like the one inside a cut diamond. The sun's corpse crystallizes from the inside out. Its final form, still billions of years from complete, is a diamond the size of a planet, glowing faintly, dimming toward red, and then toward nothing at all. The theoretical end of that road is a black dwarf, fully dark and fully cold, and the universe has not yet lived long enough for a single one to exist. That is what it will actually do instead. Not shatter. Soften. The myth was always louder than the truth, and the truth turned out to be quieter and stranger and somehow kinder. There is no scream at the end of the sun. There is a light that dims by degrees, a fire that seals itself away, a skin breathed off in glowing rings, and an ember that freezes into crystal and waits in the dark longer than the stars around it will last. So the thing that woke you this morning, the warmth on your skin, the light that has crossed the sky above every person who ever lived, will not end in fury. It will end in patience. It will grow bright and swell and let go of its outer self, and then it will simply glow and cool and quiet down. An Earth-sized crystal cooling in a dark that has already forgotten how to be afraid of it. There is comfort in that, if you let there be. Nothing about this is close. Nothing about this is sudden. Every stage takes longer than the whole history of the human race, longer, in the end, than the universe has yet been alive. You will not see it. No one will. It is a slow, gentle, private ending, unfolding across timescales so vast they feel almost like stillness. The sun is not a bomb waiting to go off above you. It is a warm and steady thing, halfway through a long life, that will one day lie down as a cooling jewel in the quiet. Let that be the last picture you carry down into sleep. Not fire, not fear, just a small bright ember, earth-sized, crystalline, glowing softer and softer against the black, in no hurry at all to finish. The star will settle, the light will soften, the dark will keep it gently, for longer than anyone can count. There is nothing left to do now but rest, and let the sun keep its slow appointment with the future, while you keep yours with the night. The numbers can wait, the stars can wait. Everything out there is moving so slowly that it will still be there, unchanged, long after you have woken and long after you have forgotten this. Close your eyes. Let the warmth of an ordinary patient star settle over you. Sleep well tonight. Good night.